afternoon, everybody. Well, thanks for coming along to the ABI's Tuesday seminar. Today our guest is Dr. Ðula Nađ from the University of Zagreb's Laboratory for Underwater Systems and Technologies. We've been very lucky to become involved with them. We were more or less married to them through the Office for Naval Research. They knew about our ability with soft sensors for measuring the movement of the human body. These guys are developing interesting robots, underwater robots. So there's the opportunity there to put the two technologies together and to make a system which can actually understand what the human's trying to do underwater. And I think Ðula will talk a little bit about that, but he's mainly here to talk about his laboratory's great experiences with developing exciting new underwater technologies. So I'd like to introduce to you Dr. Ðula Nađ from the University of Zagreb, Croatia, who's going to talk to us about their new systems. So
okay.
Thank you, Ðula. Yep.
Okay. Thank you for the introduction. Hello, everyone. If you have any questions during the talk, please just feel free to stop me and maybe ask if something needs to be clarified. I know that I'm speaking a bit, not so well English. Yes, and if you can't see me, if you're there, maybe come forward. It will be easier. So my name is Ðula Nađ from the Laboratory for Underwater Systems and Technologies, and you've already heard. And I'm here to talk to you first about our university, of course, but then a bit about tracking and how we got to diver-robot interaction with our projects. So most of you probably know already where Croatia is, or at least a general location, but we will refresh your memory. And I will talk a bit about the University of Zagreb and also about our laboratory, what we do. After that, we will continue to some interesting things like tracking, localization, aiding for divers and also for underwater vehicles, and show some projects that we went through in which we actually first started with vehicles and then ended up at the divers. And then I will talk about the Cognitive Autonomous Diving Body, or CADDY project, which was actually our first really diver-robot interaction project, a large one that we did. And based on some lessons learned during this project, we were able to now acquire this ADRIATIC project that we have with our partners here at the University of Auckland and perform another set of improvements towards getting this more product ready rather than just doing basic research. So let's get started. So to refresh your memory, I've shown here a few pictures from Croatia. And basically there are a lot of pictures, so I didn't know which to choose. But I took some of the most memorable. So if you like history or Game of Thrones maybe, you know about Dubrovnik. This is a medieval city in Croatia on the south part of the coast. If you follow football, you know our national team, or probably some of the players like Modric, and you know that they probably won the silver medal last year, right, on the World Cup. If you like nature, like beautiful nature you have here also in New Zealand, then Croatia has a lot of beautiful inland nature and a very developed coastline with thousands and more islands, and also a mountain range that is very close to the sea. So this is a nice way to walk, looking at thousands of islands from the mountain. And finally, if you really like Christmas decoration, then you will be glad to hear that Zagreb has won this award for the Advent, for the best organization. So best Advent in Europe is actually in Zagreb for several years already in a row. So since we're also engineers here, I guess, we should also have some numbers. So basically you can see that Croatia is located in south central part of Europe. It's a quite small country. It's like 4 times or more smaller than New Zealand. The land area is around 56,000 square kilometers. The sea area is around 30,000 square kilometers. And this sea we actually call Adriatic, similar to or same as the name of the project. Our population is 4.3 million, so a little bit less than New Zealand. Our main capital is Zagreb, in the inland of Croatia, and it has around 800,000 people, so half the size of Auckland, I guess. right? And university-wise, we have 2 universities inland and 5 universities at the coastline. One of those, or the biggest university of those, is the University of Zagreb, where we come from. Myself and Igor here, that came to visit Auckland today. And basically, this is not only the oldest university in Croatia, but also the oldest university in Southeastern Europe. It has a lot of undergraduate and graduate programs, and it usually outputs around 430 PhDs pretty much every year. And it has 50% of all students in Croatia, so that's about 40 to 50,000 people. And it also outputs 50% of all the research output of Croatia. So it's quite a big university with a lot of faculties. One of those faculties is our Faculty of Electrical Engineering and Computing. We have around 600 freshmen, new freshmen each year, and around 500 postgraduate students. We have a lot of employees, like 530 employees, of which 200 are some academic staff. And the university is divided into 12 departments that pretty much cover all these aspects of electrical engineering and computing. One of these departments is the Department for Control and Computer Engineering. This is our department that was established in 1954 by Professor Vladimir Muljević. Currently, it's divided into 4 laboratories. A laboratory for robotics and intelligent control systems that deals mostly with humanoid robots, industrial robotics, and also aerial robotics. A laboratory for autonomous systems and mobile robotics. They usually deal with land robots, but also now started to do human intent and such recognition. And the third laboratory is laboratory for renewable energy systems, so they basically deal with wind and solar generation of energy. And finally, we have our laboratory, the Laboratory for Underwater Systems and Technologies. It's a quite small laboratory, I would say, compared to the others in our university. We have 2 professors, Professor Vukic and Professor Nikola Mišković. We have 2 postdocs, Antonio Vasiljević and myself, and 5 PhDs, Ivan, Nadir, Filip, Anja, and Igor, who is here with me. 2 academic staffs, Ivana, and administrative staffs, Ivana and Ana Maria, and 1 technical staff, Nikica. So just to see, because some of them you might see next year here or in 2 years, so just remember them. So although we are a small laboratory, we aim to cover a large area of research. Our primary experience is in navigation, guidance, and control systems. First, it was navigation, guidance, and control of ships. But now, in the last some 15 years, it started to be navigation, guidance, and control of unmanned underwater vehicles. So basically, we moved into pure robotics, creating new robots and experimenting with them. So it was natural for us to expand from navigation, guidance, and control, because robotics itself is quite multidisciplinary. So the first step was to have multiple vehicles, because to having multiple ships is quite expensive, but multiple small vehicles that are quite cheap, it's very easy to have, and you can do a lot of fun stuff with them, like cooperative control, formation control, do some marsupial robotics, etc. Usually we would buy these robots in the beginning, but during the last 6-7 years, we started to design our own robots, because that's the best way to fit them for any project requirement. So you can easily write a project and then just create a vehicle for it, because it's not that expensive. It's actually more expensive for us to buy vehicles, because underwater technology is quite expensive in itself. As of 5 years, since 5 years, we have human-robot interaction. We started this with the CADDY project, and also underwater perception, because you really need to find this diver in the water and be able to communicate with him. And as sensors are now getting much cheaper and smaller for underwater, we also started looking into Internet of Underwater Things. So the Internet of Things on land is already picking up, so it's time for it to go underwater anyways. So this is a short introduction about who we are and what we do, and from where we come. And now we can move to some of the projects that we do. So our first interest was in tracking and localization aiding of underwater agents in general. So why this fuss about all this underwater localization? So the thing is, if you're on land, outdoors, and you have a global navigation satellite system, you pretty much know your location. Once you move indoor, you already have some problems. You need to use either a camera, you maybe need to mount some new sensors inside the room to get your location. And when you go underwater, it becomes even more complex. Now you have a 3D environment where the visibility is very bad. You lack global navigation satellite system completely, as soon as you go underwater. Since the GPS or electromagnetic signals in general are attenuated very much underwater. So you're moving, if you are in a water column, you don't really have any reference to where to go. So it's useless to use a camera because you don't have any reference. And even if you're on the bottom, you could have some featureless bottom, and then also very hard to navigate a vehicle in such an environment. There are some alternatives, and these alternatives are usually quite expensive sensors, starting at some like 15,000 New Zealand dollars and up. These are acoustic sensors like the Doppler velocity logger that would give you some velocity of the vehicle relative to the sea or relative to the bottom, if you can reach the bottom, if you're very close. And you also have some localization system acoustic that give you the distance or the bearing towards some beacon that is either georeferenced underwater or it's either floating and has access to GPS, so it knows its position. So this is how you can get some position. These are usually very slow systems, especially the acoustic localization. Maybe each second or each 2-3 seconds you can get some position, and the farther you go, the longer it takes, of course, because of the travel time of the acoustic signal. So even if you manage to get these expensive sensors, when you go for scaling, it gets very, very expensive. And then we have to look actually into some alternatives that we can do to get good navigation and maybe share this expensive sensor between multiple vehicles. So you can imagine if for an underwater vehicle with these sensors, also the navigation is like challenging, that for a human diver that has only maybe a compass and a pressure sensor, it becomes even more challenging. Especially when you think about the low visibility underwater and you usually use your vision to get around and navigate around the room or around outdoors. So in water you have usually visibility maybe 5, on best of days maybe 10-15 meters. Even especially in the Adriatic, maybe in oceans I think it's much less. And so it's very hard to see and have the reference. Also the bottom usually looks similar. If you don't have enough experience and training, it can be quite hard. But there are procedures for training divers to actually be able to navigate even in very murky waters, just using a compass and a pressure sensor. However, currents are also one of the problems here. If you don't see the bottom, you don't have a reference of movement, you could be carried by this current not even knowing it. So divers have also similar problems, but even worse problems than underwater vehicles in navigating. And the other thing about divers is also they are human beings. So the environment underwater is not so friendly to human beings. You need to carry equipment. You need to have a tank with limited air supply. You cannot just go up and down, because during your dive you accumulate nitrogen in your blood. You also take in a lot more volume of air into your lungs that you would on a normal pressure. So if you were just to go up, at any sign of danger, you could easily get like a decompression sickness or even pulmonary embolism or something like that. So that's why usually divers try to dive in a group. So they always have like a diving buddy, somebody who could help out if something happens, so they don't need to surface. Or if they are in panic, he will keep them down not to surface. Or also, when you take a lot of nitrogen, you start behaving like you are drunk. So suddenly you will go off somewhere. So sometimes it's enough to have this buddy there and maybe push you 1 meter up so that the nitrogen starts installing back. So and you get sober, you sober up. So he just pulls you out of this drunkenness. It's called nitrogen narcosis, this condition, when it happens. But even when they dive together, there is always some risk that these two bodies could separate. In recreational diving, it's not such a problem. Usually the agreement is, okay, once this happens, then we do a safe dive out. Both of them dive out. When they see each other, maybe then they can continue the dive or actually call it off, because you don't get a lot of chance. Once you get down, you can maybe be there 20, 30 minutes at max if it's a very large depth, like 30 meters or something. So in other situations, this body separation could be still dangerous, and then you have 2 divers to worry about. So this is why we actually started the CADDY project back then. So this relation between underwater vehicles and divers, and that we could combine because they have the same problems, that we could give a same solution for both. This didn't occur for us at first, of course. But we had one project where we actually noticed these similarities very easy. So it was some 10 years ago, autonomous naval mine countermeasures. So the basic idea is you want to remove the manned ship from the minefield. You don't want people there, so you need to ensure crew safety. And it also reduces a lot of the cost, because if a ship is destroyed, it's very expensive, and a lot of lives are lost. And if a small autonomous vehicle is destroyed, well, you just buy another one. It's not such a problem. At that time, there were some alternatives where usually you would have a remotely operated vehicle that was equipped with a sonar and with some expensive sensors. You would be a little bit off the minefield, but still with the ship. Put it down, the operator would dive into the mine, and then neutralize the mine. So for this, you still needed a ship, so they said, okay, let's have an autonomous vehicle that could detect the mine by itself, and then it can neutralize it. This is fine, but if you want to detect a mine, you really need a very good sonar, and a very good sonar is also a very expensive and large sonar. So it didn't make much sense to destroy it. So our solution, at least in this project that we investigated with NATO, was to combine a small, cheap underwater vehicle that would be just equipped with a compass and pressure sensor. And basically, the concept was you would have either an autonomous surface vehicle equipped with this sonar, or an underwater vehicle with a sonar that would carry this vehicle. When it finds the mine, it would drop the vehicle into water, detect it in the sonar, so use this expensive sensor to provide localization aiding to the small vehicle and guide it to the desired target. The communication that is here is just acoustic communication again, and the vehicle had just a cheap acoustic transducer. So basically the communication was one way. So the idea was, okay, we can place it near the mine, we can activate it when we want, we can go off, because acoustic communication, you can easily achieve 1-2 kilometers, so you can go to a safe distance. You can maybe use it to position this overnight in the minefield, and then when you really need to do the attack, you activate them and clear the minefield and go out with the ships. So there were a lot of applications for such thing. But then we thought, okay, so this small vehicle has a compass, has a pressure sensor. It kind of sounds like the same sensor suite that a diver has. So why shouldn't we try this with a diver? So we took a small diver tracking localization aiding proof of concept project to see what will happen. So we decided first to go with a surface vehicle. We could either mount the sonar on it or maybe some other localization device. What we did create this small vehicle and mounted an underwater localization system. It's a USBL, a short baseline system. Basically, this system communicates with the diver through another modem. So the diver has a small beacon on the back that can communicate, and you achieve simultaneous localization of the diver and simultaneous communication. We added a simple commercial tablet. We just put it in a housing and used an inductive pen to use this tablet. We created an ability for the diver to actually chat with the surface, and the surface could send the diver back some commands on answers. And since the vehicle is equipped with a GPS and this localization system, it can actually know the diver's position and send it down to the diver. So the diver has his own position on the map, and if he needs to go to some point, he can simply look at the tablet, position himself, and go there. This was much easier than looking at the compass and then counting how long you go, etc. Also, this vehicle was doing the tracking just because to ensure that the acoustic channel is actually vertical or short as possible, so that it is quite reliable during the time. So the divers seem to think that this is a very good idea. The thing was that, okay, so this vehicle tracks and it gives you position, that's good, but it doesn't help you a lot more, you know. Okay, if it's above you, it's maybe like a diving buoy. So you have like a private satellite. So they wanted a bit more. So we were thinking, okay, what could we do? And one option was, of course, let's try to introduce another vehicle, you know, just throw another vehicle at the problem. And so we decided to still keep the surface vehicle and add one underwater vehicle. Now this vehicle would be like a diving body, so basically it would always be close to the diver. Therefore it could do better localization aiding, so give better positioning to the diver. It could also perform mission monitoring, because it's close to the diver, it can record it with a video camera, not only with the sonar. And finally, it would be a very good tool, so the diver could use it as a tool, you know, record it or drag it around or tell it to do something. And of course, the diver himself is very good at scene interpretation and manipulating small objects, and this is very hard to do with the underwater vehicle. On the other side, the diver would need to carry all the underwater vehicle sensors, and that would be cumbersome for him. So basically, we have kind of a diver-robot synergy here. So that's why we decided to actually call it BUDDY. This project was, as I mentioned, called CADDY. It involved the 7 partners down here. And we got some 3.7 million euros to try and do some testing. So when you look at this possible diver-robot synergy, there are many avenues that you can go down. You know? So we had to select a few. So we decided on these 3. The first one was diving observer. So we wanted to collect as much as possible, as many data as we can about the diver, about the whole dive. And in the end, you could give this to the diver. He could get some feedback, see what happened during the dive, and he could always log his dive and have it for each time he needs to look up the data. This was especially aimed at technical divers that do some work, or archaeologists, marine biologists, etc. So what we did here was, again, try and create a new vehicle. So we made the AUV that is omnidirectional, so basically it can move in search, sway, and yaw at all the time independently, which was required for future use, like for a tool, etc. It had all the sensors needed for absolute localization, and it had the sonar and the camera there in order to record the diver. On the diver himself, we of course had the acoustic modem, but also DiverNet system, like so many IMU sensors, in this case 14, for a full pose reconstruction, so that we could actually combine this with physiological parameters like breathing and heart rate, and detect when the diver is in distress. And then the system could actually emit a signal either to the dive master that there is some problems with the diver, or even in the future, you know, it could intervene and help the diver. So since we already had these sensors, of course, we needed to track the diver, we needed to detect it in order to collect all this data. So the 2 main sensors that we used for detecting the diver were the sonar, as I mentioned. So it is a 2D sensor that gives you basically range and bearing towards a point. You have no information about the depth of the diver. This you need to get from another channel. You have some medium range to operate here, so 15, 20 meters, you can still detect the diver. You know, this blob that is swimming here. And the good thing about the sonar is it's sensitive to visibility conditions. So basically, if it's murky water, you will get the same image. Even if it's clean water, I mean, you don't see any difference between clean water and murky water in the sonar, at least. The camera, we had a stereo camera, and we used this to get the complete 3D position of the diver from a point cloud. However, as you can see, even here in very good visibility condition, when the diver is close, some 3 meters from the vehicle, the point cloud is still very noisy. So the problem with the camera is it has a very low range. So up to 3 meters, you get some robust measurements. After that, it starts to get a lot of dropouts and noise. So basically, this is because it's sensitive to low visibility, just as human vision. So once we had all this data, then we could actually give this to the diver. So basically, he could take a look of all the video streams on the vehicle. There were a few more cameras than this one. And he could see the sonar recordings. And also, we gave him a 3D replay of the mission, where he could actually see his relative position to the vehicle, and also all the information from the post-estimate sensors. So once we had all this information about the diver, now we decided, okay, we should now try and help him during the dive. So the next move was, let's try and create a dive guide. So basically, the diver should have his tablet, select some point, and tell the vehicle, okay, guide me to that point, because why would he look at the tablet all the time, and aim for this point when the vehicle could do it? And so there are many ways you could do that. And of course, one normal way would be maybe you exchange some master-slave roles. When you want the vehicle to guide it, you give it a master role, it starts and goes to the point, and you follow it. But what happens if the diver decides to go off, or then he needs to remember to stop the vehicle, put it into slave mode, etc. So again, you would have here a problem of possible body separation. So we decided, okay, we will not do any master-slave roles. We'll put the diver in charge and see what we can do out of this. So we decided, okay, let's create a circular path connected with the diver. We want the vehicle to converge on this circular path. Once it converges on the path, it can maneuver on this path without any danger of hitting the diver. So that was a nice first step. When the diver is moving, we said this path is moving with the diver. So inherently, you get tracking because the vehicle maintains its position on this circle. And the good thing about positioning it on the circle, since it's omnidirectional, we could easily keep any position of this circle and always look at the diver at the same time. So when the diver wanted to do this guidance, he would select the point, the vehicle knows the point, knows where the diver is, so it would position itself between the target and the diver. This way it would act like kind of a pointer to the diver on this circle. And the good thing is that the diver can do whatever he wants. When he wants to track the vehicle, he will turn towards the vehicle, swim towards it, and the vehicle will guide it. When he wants to do something else, he can swim off, but the vehicle is bound to the circle, so it has to travel with him. So the risk of any separation is fairly low here. Once we had this done, we did some tests in the pool that I want to show you maybe here. These tests were done on the program review. So basically here, the diver was turning in place, and the vehicle, as you can see, is moving in a circular fashion, so staying on this circle. In this case, it will come in front of the diver. Once it's in front of the diver was instructed to continue straight along the transect. So this was just a simple test to see, okay, is the vehicle maintaining its position or the distance from the diver as required? Is all data collected as it should be? And we could get some performance indications from that. In this case, actually, I should mention there is no guiding. So the vehicle is just set to be always in front of the diver. So it actually detects the orientation of the diver and goes in front. When the diver was at the end of the transect, he set a point and started swimming back on the transect, ignoring the vehicle, so that we could check if the vehicle is adjusting. So you can see as the diver is moving, the vehicle is slowly adjusting to point towards the given point. And the given point was somewhere outside of the pool in the direction of the door, I guess. So it looks like. And so this was quite a simple test where we could show that we would be able to point to the direction of the target, and the diver could use this as a pointer. And then we asked ourselves, okay, what more can we do for the diver? So we were adding a lot of functionalities like area mosaicing. So maybe the diver wants to do a mosaic of some area, so he just commanded the vehicle, create me a mosaic. The vehicle had a down-looking camera, would go over the area, create a mosaic. Maybe he wanted some photo documentation, so he could command the vehicle to take a photo. Or maybe he wanted some tool from the boat, so that was a nice functionality. So he could just instruct the vehicle, okay, go up, bring me the tool, and come back. This way, he doesn't have to dive out, and he doesn't lose a lot of time by doing that. And the only question was, okay, how will we communicate with this? So one option is, of course, was this tablet, But the other more fun option was, let's try and do like gesture recognition. So we extended the diving gestures with a lot of new symbols. And the diver would usually come in front of the vehicle. He would sign these symbols. The vehicle would show actually what it recognizes on its own tablet. Once it has had a complete sentence, then it would ask the diver, okay, you asked me to go to the boat, pick up. Do you want me to do this? And then he would confirm. Once he confirmed, the vehicle would go up, go to the boat. And then when we simulated adding the tool, it will come back to the diver. So these are some of the things that we did in this CADDY project. There are a lot more, but these were the most interesting with a lot of videos and movement. So I put those. But also the important part of the project is that we learned a lot of things, and we noticed what we will need to continue down this road, what needs to be changed. And for example, on the detection front, we noted that the stereo camera is very susceptible to turbid rotors, and that we need to somehow find new algorithms in future that can only rely on the sonar. So to use the sonar to get the exact position of the diver, but also the orientation of the diver, and maybe even estimate the pose of the diver. And we needed this, of course, if we wanted to improve another interaction and collaborative actions, right? So if you want to do some picking up of some equipment with the vehicle, then the vehicle really has to know a lot about the diver orientation, pose, what the diver is doing in order to pick up this object, to synchronize this action. On the localization front, we noted that there is a lot of logistics in putting, you need to put 2 vehicles in water, then go synchronize, then all of these are tracking, going. So a lot of things that the diver has to do, and all of the vehicles are a bit on the heavy side, so the diver, you would need at least 3 or 4 divers to get 1 diver into water, And so after this one gets into water, the other 3 don't have anything to do because they don't have enough people to put other vehicles into water. So we decided, okay, we need an underwater vehicle that will be standalone, and it could have a simple localization mechanism, because we still want the error in navigation to be bounded. So we will need to investigate into some acoustic solution that are cheap and easy for the diver to deploy. Maybe you just drop a reference point and then use this to bound the solution in your area of operation. On the gesture recognition side, were all these problems that we had with the camera, but also sometimes it took quite some time to recognize the gesture, so the diver would get bored, and then he would change the gesture, and then it would take even more time to detect the gesture. And from the vehicle design perspective, as I mentioned, portability was a problem. Safety, the vehicle has 80 kilos, so if something goes wrong, it could hit the diver or it hurt him. So that was not a good option. So we needed to reduce this in size. So based on these lessons learned, we wrote another project. And it's called Advancing Diver Interaction Capabilities. And we have this project with our partners here at University of Auckland. It started somewhere October last year. And it's funded by Office of Naval Research. So the basic idea is take the best from the CADDY project, improve what you can, and try to bring this basic research towards application. And applications here, when I say, I mean search and rescue, explosive ordnance disposal, and all these applications that are more military or Coast Guard, related, just because the vehicle itself is still on an expensive side. So it's not so interesting for recreational divers. But this could be and should be another step to bring down the price of the vehicle so that even recreational divers or diving clubs can buy such things. And we are actually doing that, but for the surface vehicle. So after 6 years now, the surface vehicle is going into a commercial phase. So we hope maybe in another few years that we will get this into a commercial phase. So I just took a few improvements that we aim to do in ADRIATIC. So the vehicle design, some gesture recognition, and wearable sensors on these 3 fields. We will do improvements for sure. These are the first steps in our project. So currently, there are many handheld navigators for divers on the market. And these are all optimized to be quite small dimensions and have pretty much all the sensors that we actually had on the body vehicle in the CADDY project. So their only drawback is, okay, they have no absolute localization, so the error is unbounded. So usually they use a floating buoy with a GPS. They put it up, get a fix, and put it back down. So it's tether management problems, and etc. And it also has to be carried, as you see, in 2 hands. So you need to put it down. So you're close to bottom. You can easily lose it if you're not close to bottom. You just falls down because this one is negatively buoyant. And so the solution is, okay, let's use the small dimensions and all these sensors that we can, and maybe expand it with a propulsion skid, so that we could take the handheld unit that divers already have. We would mount maybe the propulsion skill around it. So then we could add all the autonomy we had in the CADDY project, more or less. If we combine this with a small, cheap localization sensor, so as I mentioned, something like an anchor that you can drop to get a reference, then you have a bounded navigation. It can last for a longer time. It can also be used pretty much as an autonomous vehicle if you want it over the time. So on the gesture side, our partners here at University of Auckland will develop an intelligent underwater glove that does recognize some static and dynamic gestures. All the processing is done on the glove, and the glove also provides haptic feedback. So you don't really need to look at the tablet anymore. You get haptic feedback, and it's much easier for you, more natural. And we intend in the ADRIATIC to maybe get rid of the tablet completely. The best thing, of course, is no need for visual processing on the body. So you don't need even line of sight between the 2 vehicles. It could be 100 meters away. You could still do your command, come here, and the vehicle would come back. For example, if they are not deployed at the same time, they don't dive down at the same time. There are minimal acoustic transmissions because no raw data is sent, so just one command, so maybe a byte or 2 of data. This is very good because acoustic communication is very low bandwidth, so 100, 400 bits per second if you want real time. You can go a bit faster if you do buffering, but usually it's very, very slow compared to Ethernet as such. And of course, there is no need for full face mask. This is one alternative that we could have for gesture recognition, is maybe when you talk and you say the gesture, you say what you want, what commands the vehicle should do. But then you need a mask where you can actually talk all the time, which is usually maybe expensive, not for the military, but it will be expensive for recreational diver. And finally, here at University of Auckland, the development is also in embedded sensors. So using large stretch sensors that could be maybe put into the diving suit. I don't know if you remember, there was this video with the 14 IMU sensors. You probably saw that there were a lot of cabling going around on the diver. Well, it's not very safe nor ergonomic for the diver. You can easily get entangled or just break off these IMUs. So by putting the sensors in the suit, it becomes quite natural for the diver, and you still have full pose reconstruction. And also the good thing is no magnetic sensors. So if you want to use pose reconstruction with the IMUs, you do have to use magnetic sensors to get all 3 angles, right, roll, pitch, yaw of the joint. And it's very hard to actually, constantly calibrate 14 IMUs when you have a stainless steel bottle there and other equipment with the diver that is moving around and maybe not static. So as you may be seen in the replay, there are some errors in the pose estimation just because of this magnetic sensor. And apart from this, we'll probably do a lot more improvements, I hope, that we can present the next year or next 2 years, actually. And this is all from me. Thank you.
Thank you very much. That's really interesting. So are there any questions for our speaker? Yes.
Thank you for the talk. I was wondering what sort of stereo reconstruction algorithm did you use for 3D reconstruction? And have you considered combining sonar with stereo for your reconstruction?
Yeah, it's it was one of the considerations, but inside the CADDY we didn't make it. We didn't do it, but was one option to maybe improve. But how do you have any idea how you would do it? Because it's one is a 2D sensor, so basically you get some ranging. Yeah. So you could use it maybe to isolate, because you get more point clouds in the water. So you could maybe isolate
You can
diver.
calibrate the stereo camera with a sonar sensor to know where the position of the sensor is compared to the camera.
Oh, you mean like intrinsic calibration?
Yes,
Oh.
extrinsic.
Extrinsic. No,
And then you can map from one to the other one to find the location of those.
no, I mean in the filter that we had for diver estimation, we do fuse the measurements for camera and from the sonar. We do know the locations of the sonar and all that relative to each other, and also when we fuse this data inside this, then we achieve actually what you are proposing, right? We combine all this data in one filter. Also depth measurements that maybe on some measurements that we get through acoustics. This was all combined in one filter.
So
That yes, but I thought that you meant like to improve the point cloud.
Yeah, this was what I suggested. Then by knowing where the position is, you can use that to find the corresponding points between the stereo cameras, because you can match the sonar to the images of the cameras, and then you can find corresponding points between the stereo cameras and the 3D construct.
Yes. I don't know if they didn't combine it that way. They did use output from the filter just so that they know in which part of the space to look for the diver, because when you're near bottom you would have even more point clouds than you've seen in the image there.
Thanks.
Yes.
Really nice talk. So thinking about the work that you guys have done on sensing, I'm wondering if you've considered, so for the application of zero visibility environments for divers, if you've considered haptic feedback for giving divers in a zero vis environment information about their surroundings based on your sensing and sort of navigating a diver like in a wreck diving scenario.
Okay, yeah, that sounds interesting, but no, it was not considered. So you mean like to sometime by touching, giving some sense of the closeness of objects, right?
Yeah, closeness as well as, I guess, navigation. So in wreck diving, if a diver disturbs the silt
Yeah,
that's
okay.
down there, then they can easily create a zero visibility environment for themselves. So if there's some kind of important task that needs to be done and they're in zero visibility, what they resort to usually feel. But when you're at something like 60 meters of depth or more, you've got nitrogen narcosis, and so feeling around is
Well, might be.
it's only so reliable.
Well, it's interesting, yes. But we didn't get into going into shipwrecks with the vehicle yet. So when we have that,
Next round.
then
Yeah.
next grant.
The project is more or less at the start. We're having our first meeting, and we've got now at least the ability to. We're building a glove for underwater for that, but clearly the haptics and everything else could come in later. That'd be a great idea.
Yeah, it is good idea.
Can you tell us this product? You have the CADDY and the surface system.
Yes.
Now the surface system is now being prepared for productization. It's going to be sold.
Yes.
Can you tell us about that? What it can do?
Well, basic idea, it does exactly what I shown you there. No? It can track the diver, act as a diving buoy, and give diver position information and relay any information from the diver to the diving ship or master.
So what you're going to sell, the diver will have a tablet and can then communicate with the surface through the surface buoy.
Yes, if they are interested, we will sell that.
Which also follows them around. So
Yeah.
it acts like a safety buoy as well. You can
Yes,
hang a diver flag off the top of it.
Yeah, that's also. But there are a lot of practical problems when you go into it. Actually, it should be smaller. Now it's a bit bigger. We also have like a smaller version idea to make it. But then it's a problem. Usually they, how people, when they see this buoy, then they come, cut it, and take it away. So we have one of the divers asks, okay, it's an expensive thing, if I pay for it like 2,000 euros, and it's floating around and people will just take it for sure. A lot of problems.
Explosive charge on it.
Could be. Or they could just, anchor the ship to that buoy, sometimes it happens, You drag a buoy, where you dive or even you spearfish, and they just come and just tie their boat to this buoy, and then you're standing there, going nowhere. So a lot of small, interesting issues. commercialization.
Any problem with the acoustic localization in terms of structures like for rocks and also geothermal kind and stuff like that?
Okay, so there is a potential for multipath, but if it's close to the diver, then not a lot of multipath. If the diver goes, for example, if he's diving around the shipwreck, so then you could have coverage. But then, of course, if you add, you can tell the vehicle what the mission is and what is happening there. So the vehicle could always position a little bit off. It will still have not a vertical directly, but it would have some slanted access to the diver. If you go inside the shipwreck, then you will not have any acoustic communication at all, I guess.
I guess in that case, you're inside a shipwreck anyway, and you're otherwise.
Oh yes, but maybe you want to chat, or maybe in the future you want to take a selfie and send it.
I was wondering if things like fish, if you dive in an area with fish, does that interfere with the sonar and the movement of the stereo camera stuff?
Well, if he goes into a flock of fish or however it is called, well, maybe it would be hard to see the diver then. But usually, I mean, even I think in the video I showed, there might be some fish because we were in some marine pool that had fish around it. So, but I don't think they will have highlights, but they move much faster than the diver. And usually when the diver comes, he scares them away because he's very noisy, especially when he's just doing normal scuba equipment. So fish are quite scared of that, so they go away. Okay.
One thing you should do is do a little bit of an advertisement for the annual conference in Croatia.
Yes, that's true. I
Breaking the
didn't
surface.
put that in. Yeah.
Was that?
Yeah, I didn't put the slide in.
Yeah,
but
we attended this for the first time last year. It was wonderful to meet. This is it the first week of October?
Yes, it's usually always the beginning of October.
Bioengineering, which is right on the Adriatic coastline, and you have people from all walks of underwater technology life all meeting together in this one resort.
Yes.
So you want to say something about it?
Yeah, so basically this is a conference/workshop that it started as underwater archaeologist or underwater roboticist and underwater marine biologist, actually underwater biologist, but now extended to security, underwater security and geology and such. So it's a very big conference, usually like 200 people, and lasts for 1 week. All lectures are invited lectures, so usually people who are, well versed in their field. So you get a lot of new information. You have a lot of hands-on demos in the afternoon, usually where either companies present their product and then you can try this product, or maybe some labs present their projects and you can then come, maybe participate in this project. So it's quite interesting. The social events are also quite interesting, right?
You can go snorkeling too.
Yes,
right
of course.
there. If you're lucky, you might see a Mediterranean fanworm. I was telling them that all the other Mediterranean fanworms are in our harbor.
Yes, so if you're interested, we can talk later. I can give you some information. So beginning of October in Croatia at the coastline. So Biograd na Moru, it's near Zadar, maybe a bigger city, between Zadar and Split, something like that. So if you're interested, yeah, please.
Yes.
So you mentioned about the problem of the diver carrying the tablet or whatever the display that he is having. So did you think about using augmented reality swimming glasses that can be
Yes.
used as an interface?
Yes, we were thinking about it. I was suggesting it for this project, but yes.
And it will be cool to have the stress and clouds interface with that so that everything can be.
Yes, would be quite interesting. Although I would prefer to buy such glasses, but didn't find it really. There were some campaigns like Indiegogo, Kickstarter. Didn't go through. Didn't seem like there is much interest. But I think that it would be a great idea if there is something like that we can buy, because we don't have the resources nor the knowledge, I think, to develop this straight out. At least our lab didn't do anything with these polymers and with such augmented reality materials.
Well, looks like that's it. So thank you very much for coming and presenting your work to our institute, and welcome to Auckland.
Thank you for having me.
And hope that you have a profitable week with us. They fly back, I think, on Monday, is it?
Yes, on Monday. Yes.
And there's going to be some sort of adventure this weekend, some New Zealand adventure.
Yeah, for sure. Yeah.
So thank you very much, Ðula.
Yeah. Thank you.